All right, and so now we are ready for another one, another improper integral that even more dangerous than the two forms that we have seen previously. Okay, so now let me bring up a problem as following here. And so we gotta watch out this integral, really carefully. All right, so how about we have an integral from 0 to 3 on the function 1 over x minus 1. All right, so this integral, right by first look right here, right at first sight, it seems to not run into any of the situation like the two forms I've introduced earlier. The function is continuous at 0. Okay. The function is continuous at 3. So both upper and lower limits of the integral problem here have no problems with the function. The function is, in other words, continuous at both the left point and right endpoint of our integral interval. Okay, so that for that reason, people can start rushing into the fundamental theorem of calculus and do the following. Well, with a little easy substitution method, we can use a U substitution for this, or anyone viewing this video should be fluent enough so I can see that the antiderivative of 1 over x minus 1 can simply be natural log of x minus 1. And then so without realizing, without noticing, or without seeing that we have any discontinuity at the two endpoints here, so we feel safe. We feel safe that we can just apply the fundamental theorem of calculus directly here, and then so in the next step I am tentatively going to evaluate this from 0 to 3. Okay, and so now, and then in the next step everything seems fine. We keep turning out good results, and it's natural log of absolute value of x. So here what I have is a natural log of substituting 3 into there, we have 3 minus 1 in absolute value minus natural log of 0 minus 1 in absolute value. And this gives me natural log of 2, which essentially is the same as natural log of 2. And then 0 minus 1, but in absolute value, so it's a natural log of 1 anyway, and that goes to 0 according to the logarithm property. So now our answer is 2. Okay, and we feel like we're done with the problem. Bingo, we got the problem done. Okay. All right. The sad news is that is incorrect. Okay, this is not the way how we get it done. And so now allow me to point out the reason why it's actually a dangerous work that we were doing here. Very dangerous work that we were doing here. It's all due to the fact that, well, we checked, admittedly we checked, I checked that to make sure we didn't run into the case as I have brought up in the earlier problem. So I checked with the left endpoint and the right endpoint of our integration interval, and we found out that there's no discontinuity at these two endpoints. So we feel safe that we applied the fundamental theorem of calculus. All right, but now let me bring up the graph of that function right here, and now you will immediately understand what I meant earlier by this is the incorrect solution right here. All right, so here on my graphing space with desmos.com right here, here's our function for f of x equals 1 over x minus 1. All right, f of x equals 1 over x minus 1. So for extra clarification, I can remind anyone, I can recall for anyone that this function, a function like this, has an asymptote, a vertical asymptote at x equals 1. Okay, and let me put that in dotted line right here. All right, so we have a vertical asymptote at x equals 1 for our famous function f of x equals 1 over x minus 1. And so now here's the interval of integration. Here's the interval that of the integration. There's our interval from 1 to 3. So 0 to 3, x equals 0 is here, x equals 1 is here. So apparently the function did not have any discontinuity at the two endpoints of the interval. However, now when x equals 1, and x equals 1 is unfortunately right in between 0 and 3, which is the low and the high, the limits of our integral problem. And so that's where it creates all the trouble for us right here. So let me now create the shading of the area. So think about the shading right here. Okay, we can pick any interval, but we can't go to as far as, we can't substitute in x equals 1. Okay, and then on the left hand side, think about the areas, the accumulation is going to have to be like that. So now that tells us a story that deceivingly, from first sight, it seems like the left endpoint and the right endpoint of the integration interval did not make any problem. But then now, if we look more closely, we have a discontinuity point right in the middle between the two. Right, I mean, not exactly in the middle. It doesn't have to be in the middle, but right in between the left end and the right end of our integration interval. And so in that way, this is apparently the reason why it fails like that, because now back on the graph again, and I have done that little illustration earlier. See, let me zoom it out further. And so as I drag the handle here, the amount of area keep leaking out. I'm using that term leaking out to demonstrate the fact that it's not a finite amount of, I mean, we're not sure if it's going to run into a finite amount, but it keeps leaking out. There's more area that we can accumulate in the closer I drag this handle to x equals 1. And the same with this portion right here, from 0, we can keep dragging a handle out closer to x equals 1, and you can see that there's the blue amount of area keep bleeding out and keep leaking out. Okay, and so we keep obtaining more, we keep achieving more shaded area in blue. Okay, but will the two answers here come to a definite answer? That's what we want to find out. Okay, and so now that kind of demonstration right there, and along in right here in this problem right here, brings us into the third form. I mean, another form, the third form among those that has a discontinuity, you know, in your integration formula. I mean, in your integration interval. So unlike the two previous cases, the integration interval has a discontinuity either at the one of the two ends right here, either the low end or at the right end. Here our integration interval has the discontinuity right in between that. Okay, and so now I'm gonna do another explanation of the idea, and you have seen that already. So from this problem, what I noticed, okay, still in the same problem, from 0 to 3 on the function 1 over x minus 1. And now the graph that we saw earlier point out for us that what we notice here is that there's an x equals 1 that's right inside, there's a value 1 in between 0 and 3. Okay, and then we have f of x is discontinuous. Okay, discontinuous at x equals 1. Okay, at x equals 1. So now in that way, so here's the plan to handle this problem right here. So we're gonna tackle down right at that particular problem. So we think of a plan like this. And I'm not saying equal or anything. I'm just saying in the way how I was dragging that handle earlier in the graph, then we can, why don't we produce, because since 1 is in between 0 and 3, our overall integration interval here anyway. So why don't we think about making an integral from 0 to 1 on this function, 1 over x minus 1. So this is now apparently or clearly an improper integral of one of the two types we have been introduced just earlier. And then, and of course we haven't found out whether or not this integral here is a finite or a convergent one yet. Okay, but then think about, once again, keep thinking back of that graphical illustration right there. Then we can also think about producing another integral that runs from 1 to 3. I mean, this is completely consistent with the idea of a definite integral, where you see we can accumulate from 0 to 1 and from 1 to the other end of the interval. Okay, and then if for any reason that we can find a successful answer for this, if this turned out to be finite, if this answer turns out to be finite and this answer also turns out to be finite, then we can add that, work together. Okay, so that's the plan for now. That's the plan for how to handle this kind of thing. And at least once I pointed out about breaking it up into 2 separate improper integrals here, now both of these are all familiar within what we have learned prior to this point. They are all in the 2 forms that we have learned before we arrived at this point right here. Okay, so now at this point, I'm not intending to go any further into this problem, this demonstration problem. I only want to bring up this problem to illustrate for you that outside of those 2 forms I've introduced just right before this particular one right here, then we have another one that's quite dangerous. Okay, and it causes even I teach calculus for quite some years now, but I still make that mistake sometimes. Okay, so you got to understand that sometimes it's dangerous in a sense that we have a 1 or 2 or even more discontinuity points inside of your total integration interval, and that's where it create all of that trouble. And so here the plan for that is to break it up into improper integrals that run from anywhere to the starting to those discontinuity points, and from those discontinuity points to the rest of them. Okay, and so now, as I said earlier, I'm not going to proceed any further into the problem, but now let's formulate that into an actual definition. All right. So here I'm going to start out by saying in my definition, and it's really the same definition, but I'm just continuing into part C right here. So in part C, I'm going to have to start out by saying let f of x be a function with a function that's discontinuous at an x equals c, where c is anywhere between a and b. Okay, anywhere between, and of course, let's take the fact that the function is continuous at these endpoints. It's just discontinuous at some value c inside of that interval. Okay, then in that way, now this is the third form, another form among those that has some discontinuity in the integration interval over here, the improper integral. So again, it's another improper integral. The improper integral of the form accumulation from a to b on the function f of x. But keep in mind, again, the preliminary here says f of x has some discontinuity, at least one, somewhere between a and b. Okay, so this improper integral is defined to be the sum of the integral from a to c, okay, plus the sum of that improper integral from c to b on this function f of x. Okay, but only equal if both both of these integrals from a to c on the function f of x and from c to b on the function f of x. If both of those are convergent. All right. And then in that case, and now let me move over to my other board to complete my definition. And then, so if the two integrals from a to c and from c to b, if both of those are convergent, okay, then the integral from a to b is said to be just like the earlier definition, is said to be convergent as well. All right. And otherwise, divergence. All right. So now let me get back on my other board and explain this a little more. So this equality right here is similar to how I was introducing the earlier definitions. It's only shows an inequality just as a plan that anytime we are seeing this improper integral where it looks like just any other ordinary definite integral out there having a low end and a high end, and they're both the function is both defined and continuous at these end, but unfortunately having a discontinuity somewhere in between right there, then the way to handle that's what this equality means. Anytime we see this, it means we have to start out with two, I have to emphasize that we have to start out with two separate improper integrals. That's what the equality means. It doesn't always mean, this equal that in the usual equal sense. It just means that in order to get that work, we first have to start out with two separate improper integrals. And these, at this point, we all learned the way how to handle these separately. And only when both of those, I have to underline that, only when both of these integrals, only both of those run into a finite, and see, so the shorter way of saying that now is only when both of these are convergent. Okay, so recall from our previous part of the same definition here. Any one of these being convergent means the limits, their own limits, is going to be a finite value. So, but now we need both of these to be convergent in order for that to have a value, because once these are both convergent, then that has a value, a numerical value. This will also have a numerical value. Then the overall integral here will be equal to the sum of the two answers there numerically. Okay, and then in that case as well, once both of these improper integrals that we have investigated earlier are convergent, then the overall integral here is also regarded as or decided to be a convergent integral. Okay, otherwise, now, so when I say and otherwise, this term otherwise here, it's written short, but it has a lot of meaning. Otherwise just means as long as one of the two improper integrals here fail to be convergent, then this thing here will be a divergent one immediately. And we can completely bypass looking for the final answer, and there won't even be equality holding here if any one of these is a divergent one. Okay, and so with all that logic right there, so much to talk about, but let's get to doing some actual work right there. All right, and so now in that way, I will go ahead and complete that problem I brought up earlier. So that we will understand what's going on here. So sadly, I brought up the definition here, but it didn't stay here on the board for too long. And again, I have to mention, I write the definition in a way I believe it will, make it easy to understand. But of course, allow me to skip some of the details here. And so in that way, the actual wording, can be delivered in any of the standard calculus textbooks like that. So to get the precise wording, go ahead and read any standard calculus textbook that you are using for the class. Okay? All right, so now, and this is not even an example, the next example yet. So the very last example we've done was example 4. But now I'm not even in example 5 yet. Let's look at, let's wrap up that problem I brought up earlier. So this one, from 0 to 3 on the integral from 1 over x minus 1. With that one. So now as a plan, I am going to consider 2 separate integrals. One of them is from 0 to 1, because remember, we noticed that there's a 1 in between 0 and 3, and f of x is discontinuous, okay, at x equals 1. That's what we noticed. Okay, and so now we tackle down right on that one. And by the way, for this particular problem, 1 is the only discontinuity point inside of our integration interval. Okay, and so now according to the definition, and that means it tells us that first we have to produce 2 separate improper integral. You see how improper this is? Okay, so now we run right into that problem where we immediately recognize that, hey, this function is discontinuous at 1, the upper limits of our integral. Okay, and then tentatively we need to add that. To the integral, the result from 1 to 3 on the same function, f of x dx. Okay, so tentatively we start looking into this sum right here. We start looking into that sum. Okay, but I'm not saying anything about whether this sum will equal to that. It all depends on, it all depends on how we can find out if both of these are convergent. Otherwise, if that one immediately fails, we can stop the problem. If that one goes to a value but this other one fails, we also need to stop the problem. We only go all the way to the end when both of these give us some final numerical result. Okay, so in that way, so here is how I'm seeing it. So I wrote that down, but I can even further just tear this one apart right here, and I'm going to produce an integral from 0 to t, just like how we did that in the earlier example. The function here is 1 over x minus 1, and here I'm going to let t approach my upper end from the left-hand side. Okay, from the left-hand side, and I'm completely disregarding this part for now. I'm only working on that, and let's find out. So see, there's a certain order right there. So once you picked one, I can pick this one first as well, but it's just my own decision. I picked this one. That's not really a big good reason for that. Okay, so anyone watching this video, feel free to start out with this one first as well. But now the plan here is, if this one fails immediately, which we haven't gotten there yet, if this one fails immediately, I'm going to say that we don't need to add, because the whole thing here will fail, will become divergent. So failing, I mean fail to converge, or the whole thing will be a divergent integral. If this one here passed, that doesn't mean we can find the answer to this yet. Okay, if this one passed, that means we have to go on to the next one, okay, and decide whether or not the next improper integral here will be convergent or divergent. And only when that next one is also a convergent one, then we can say, hey, so now having 2 numerical answers here, we can add them up and make that equal to this one. Okay, and so that's the logic of the work. So now back to the very first step right here. I picked that one, so let's find out if really this integral converges or diverges. All right, so seeing this now as a definite integral with an arbitrary upper limit t right here from 0 to t, then I'm using the fundamental theorem of calculus, which says I can take the antiderivative of the function, which that gives me absolute value of, natural log of absolute value x minus 1. And then I'm going to go ahead and evaluate that from 0 to t. But then I will take the limit as t getting close to 1 from the left-hand side. Okay, from the left-hand side. And so now that means further with the fundamental theorem of calculus, then we're looking at natural log of t minus 1 minus natural log of 0 minus 1. And then we will take the limit as t is approaching 1 from the left-hand side. Okay, and so this is apparently going to 0 because 0 minus 1 is a 1, is a negative 1. In absolute value, it's 1, so natural log of 1 is 0. So that term is not much to worry about. I really have what's left behind for me. It's just this part right here. So supposedly there should be one more step, but this problem in the end is only an illustration problem, a demonstration problem. So allow me to be a little skippy right there. So now I'm seeing that with this function right here, as I'm getting closer to 1, but from the left-hand side. Okay, so natural log of 1. Natural log of t minus 1 is about here where it crosses the x-axis at 2. Right, at 2, so 1 is here. Okay, we will have an asymptotic behavior like that. But getting close to 1 from the left-hand side, but in the end it's absolute value, so it means that the whole t minus 1 in absolute value here will approach 0. Will approach 0 from the right-hand side. So that means our function getting close to, so that means our function here is going to keep dropping down to negative infinity. Okay, and so now we're looking at negative infinity, which is an infinite limit right here. So that means this particular limit here is a divergent one. So this improper integral, okay, this improper integral here will be a divergent one. And so if it's diverged, now I can just now allow me to erase this work right here. Now that means, now as a conclusion, 0 to 3, 1 over x minus 1. This one here is going to be divergent. I'm just saying it's divergent. And now, knowing that it's divergent, we can just stop the problem here without worrying about finding whatever comes out for this improper integral. We don't need to do that, and we don't even need to proceed into finding a final answer, a final numerical answer for this integral, because we know it's divergent. It's not going to come to any particular value. Okay, so that's the logic of how we carry out this problem like that. So now, at this point, we are ready for pushing it into an actual example here. And through the example, we should be able to see more. All right, so now I'm going to call that example 5. And example 5, just like that, we want to, just like any of the earlier example, I want to determine the integral is convergent or divergent. Then if it's convergent, then we're going to evaluate the integral. All right, so that's the instruction of the problem again. Okay, so now here's our part A. All right, so now, so in part A, I'm looking at about x over x minus 2, okay, and from 0 to 5. Okay, so our function is x over x minus 2, and the integration interval is from 0 to 5. That's what we want to integrate over. Okay, and so once again, I'm not making any equality here. I'm just gonna, because think about it, the plan here is that we're gonna have to produce, because now I notice, okay, so what we notice here is that there's that value x equals 2, or I'm going to say the function f of x is discontinuous, okay, at x equals 2, which is right inside of the interval from 0 to 5 like that. So the function itself is okay with x equals 0, is okay with x equals 5. That means the interval looks like a closed interval. But unfortunately, there's that value x equals 2 inside of this interval, making the function here discontinuous. Okay? And so due to that reason right here, after what we noticed there, now I'm going to have to erase to make more space for myself. Now we're going to break it up as a definition. I'm going to separately consider the following two improper integrals. One of them is from 0 to 2 on x over x minus 2. All right. And I'm going to separately consider another one from 2 to 5 on that function. Okay. And tentatively we want to add, but this adding right here has to wait until, this adding really have to wait until the very end where we can supposedly get both of these into a numerical outcome, a numerical answer right there. Okay, so let's pick that one. All right, so that first one, even though anyone watching the video here also has your choice to pick the other one. Okay, but now the point is we need to verify whether or not both of our integrals there are convergent. And if only one of them fails to be convergent, then the overall one is going to be divergent. So now how about from 0 to 2? Okay. Let's look at this one here separately. So I am going to consider a limit problem from 0 to t, okay, by letting t approach 2 from the left-hand side, and the function here is x over x minus 2. That's the function we have right there. Okay, and so with this function now, and I can algebraically turn x over x minus 2 into the following algebraic expression right here. It's going to be a 1 minus 2 over x minus 2. Okay, I separated it out into two terms. And then there's the integral from 0 to t, and it's a dx. When we're taking limits, allowing t approaching 2 from the left-hand side. Okay, so if anyone questioning me how I get these separate, how did I get that separation? Simply x over x minus 2 is the same as x minus 2 plus 2. And so I just now realized I made a little mistake like that. So it should be 1 plus 2 over x minus 2. Okay? But so back from this, algebraically, I can always add minus 2 and plus 2. So the reason I minus 2 and plus 2 here is so that I can display, okay, the x minus 2 looking just like the denominator. And then I can separate it out into two terms like that, because here we have x minus 2 as a common denominator. So with the two terms here, I can break it down as, so x minus 2 cancel with x minus 2, giving me 1. And then 2 over x minus 2, that's the remainder like that. Okay? Or there are tons of other algebraic explanation for that, how I can go from here down to that. Okay? And I leave that for viewers to check with your algebra. Okay? But now once I have algebraically rewritten my function into that form with the two terms here, then that first term is easy. Okay, it gives me just a, so as far as taking the antiderivative, that first term is now a t, and I mean an x. Okay, that second term right here is plus 2 times the natural log of x minus 2, because I see the 2 on top here is the coefficient. And now I'm ready to substitute in 0 and t for here for my integral. And then, but don't forget, we need to, in the end, apply the limit operation as t is getting closer to minus 2. I mean to 2 from the left-hand side. Okay, and so now further with the calculation, I'm looking at, substituting t into the expression. It's t plus 2 times natural log of t minus 2. All right, and then I'm going to subtract further. And I'm going to substitute in 0 for x, for every x here, so it's 0 plus 2 times natural log of 0 minus 2. All right, and so that is a term in terms of t. That is another term in terms of t. This is a 0. This is a natural log of 2 eventually, and then multiply with a 2. So altogether, I'm looking at, and by the way, this problem like this, we still need to realize that it's a problem where we take t eventually to 2 from the left-hand side. Okay, and so now in my next step right here, I'm looking at t plus 2 natural log of t minus 2. And we keep turning our expression into an expression in terms of t completely like that. Okay, and so that is going to give me, and due to that minus sign, so minus 2 natural log of negative 2. Okay, but in absolute value, which is eventually the same as natural log of positive 2 anyway. So it's a constant value. So now taking the limit as t getting closer to 2, but from the left-hand side. Okay, t is getting closer to 2 from the left-hand side. And so now, okay, so similar to the explanation I've had, so this function here, this logarithm of t minus 2 will get to negative infinity. Okay, we'll get to negative infinity because natural log of t minus 2 will have a vertical asymptote. Okay, it has a vertical asymptote as at 2 right here, at 2, and then the logarithm will look like that. It crossed the axis at 3, and so as we getting closer, so when t is getting closer to 2 from the left-hand side, but the absolute value, okay, maybe in my earlier explanation I didn't explain it clear, but the absolute value is turning it positive. So that means it's the same as we're getting closer to 2 from the right-hand point, from the right-hand side, and so that's why, you know, it's going down and it keeps dropping down and to become negative infinity. So now altogether we're looking at, and that becomes a 2. So altogether our final answer for this limit is a negative infinity. It's a negative infinity. So that means this particular improper integral already failed. It's a divergent one. Okay, and so now I'm going to erase all my limits work. And all that limits work right there is just for the first improper integral. But now according to the logic we have done so far, then now it's implying that the improper integral from 0 to 2 on this function, x over x minus 2, okay, this one right here is divergent. And sadly, this one here, just now we have proven it to be divergent, is one among those that we require to be convergent in order to have a convergence value for this. So that means we have that one fail. It's divergent. So that means now as a final implication, or maybe I should get into my other board right there. That means I don't even need to work on the other improper integral, but I can get straight into my actual, my overall one from 0 to 5 right here. That beginning improper integral we were looking at, this one here is also divergent. And so here we can stop the work. We don't need to do the limits work. We don't need to evaluate the other little integral. We can just now, and we don't even need to attempt finding a numerical answer for this, because we won't be able to find one. Okay, so this in particular improper integral here is a divergent one. Okay, because one of its subintegrals, that's the way how I see that a lot of time, one of its integrals is divergent. Okay, so that's how we get part A done. That's how we found a conclusion for part A, and that's how we determined that the improper integral for part A was a divergent one. And being a divergent one, we don't need to go all the way to the end to find the final answer for that. All right, so let's now look at another one. Okay, so the one I have here, let's look at part B. Okay, so how about from 0 to 9? And the integral we have here is 1 over cube root of x minus 1. Okay, so 0 to 9, the integration formula, the interval looks just fine. We got a closed end on the left, also a closed end on the right, and closed end, I mean the function has no discontinuity at either one of these two values here. The function is fine with 0, the function is fine with x equals 9, no discontinuities there. Okay, but now sadly, this is what we notice. So we notice here that there's the function f of x is discontinuous. It's still discontinuous, but this time at x equals 1, which is inside of the interval from 0 to 9. So we have a discontinuity in there again, and we only have 1. Okay, but that's just enough trouble already. Okay, and so now, because we're realizing that, so now that, but at least the good news is once we realize that that kind of breaking up point, that discontinuity point right there, then we can produce immediately two separate integrals. One of them is from 0 to 1 over this function, okay, x minus 1, and another one. And having a plus here or not, well, I'll just go with the plus, but it really means we cannot add them here yet immediately. We have to consider the two works here separately, and then we can, if they're both successful, meaning going to become a convergent one, then we can add their values. Here I have from 1 to 9. Okay. All right, so that's our setting up right there. That's our setup. Okay, so now in that way, again, it's just me. I'm going to choose the left improper integral, the one on the left here, to get it started first. And then if this is a failing one, a divergent one, then we stop right there and saying that this integral is divergent. If this one is convergent, then that means we're going to calculate the value here, but we still need to go on to the next one. And if the next one is also convergent, then we're going to add the two answers here to become our answer for that last one. Otherwise, if that one is still going to be a divergent one, then nope, sorry, the whole integral here is still a divergent one. Okay, and so in that way, now my first integral that I'm handling right now, the improper integral from 0 to 1, 1 over cube root of x minus 1. Okay, and so this one here is apparently one of those the forms in A and B according to our definition just earlier. And so here I'm looking at, I'm going to produce a limit work. But first it's a definite integral as usual from going to from 0 to t. Okay, 1 over cube root of x minus 1. But now I'm going to have to take the limit as t approaching 1 from the left hand side. Okay, so I'm going to go with a little substitution rule over here. U equals x minus 1. How's that? All right, so du dx will equals 1, and that gives me du equal dx by rearranging the two differentials du and dx here. And so now further, it means my u1, these are value in respect to the x variable, but now we're changing to the u variable. And so u1 is 0 minus 1, which is a negative 1. u2 is a t minus 1. Okay, so now that means for this limits problem, the integral becomes the following. From negative 1 to t minus 1. Okay, and it's 1 over, it's a cube root of u. And dx gets a substitution for du right here. I mean, dx gets du as a substitution for it. And so now I'm quite ready. And allow me to erase this small work right there. And the problem is a limit problem. Getting to 1 from the left-hand side. So now I'm looking at seeing that as a u to the negative 1/3 power. So if we're seeing this function as u to the negative 1/3 power, then the fundamental theorem of calculus is going to be telling us to take the antiderivative of u to the negative 1/3, which gives me u to the positive 2/3 power, but I'm going to multiply with a fraction 3/2 in front. I'm going to evaluate this from negative 1 to t minus 1. Okay, and then I will take the limit. I'll take the limit. Okay, as t is approaching 1 from the left-hand side. Okay, and so that means I'm looking at, so now I'm going to go ahead and substitute these two values in there. T minus 1, okay, and it's a 3/2, t minus 1 in parentheses to the 2/3 power minus, and then the 3/2 again times negative 1 to the 2/3 power, and then with that subtraction here, we have created for ourselves an expression in terms of t. And so now I want to find the overall limit as t is getting to 1 from the left-hand side. And overall, I meant the limits after considering the two terms here together. Okay, so that one right there is simple. I mean, negative 1 to the 1/3 power is a negative 1, but square now, so it's going to become a positive 1. So positive 1 times the negative 3/2, that term remains permanently negative 3/2. But the first term here is, how about a 3/2 times t minus 1 to the 2/3 power, and then minus 3/2. All right, and so now taking this limit as t is getting closer to 1 from the left-hand side, this term will go to 0. Okay, so we have left behind with a 0 minus 3/2. So now it turns out that this limit here has a finite existing limit being negative 3/2. We got half of the work done. In other words, this integral here is convergent. But that's not enough. That's only like what, halfway through the problem. Okay, we found that this is a negative 3/2. Okay, so I'm gonna note it there somewhere. This is a negative 3/2. I'm gonna have to make note of that somewhere. Now I'm gonna erase clear on my board. And actually, I have just decided to make note of this on my other board right there. Just a note right there to remind myself that that this answer that we have found right here, this work we have come to the answer negative 3/2. Okay, and we will utilize that later. So now in my next work, I'm going to consider the other integral, the other improper integral. So here I'm looking at from 1 to 9, 1 over cube root of x minus 1. Okay, so for this integral, what we need to do, we set up an integral from t to 9, 1 over cube root of x minus 1. Okay, but then now I'm going to have to consider the limit as t is approaching 1 from the right hand point. Okay, so now that breaking up point, that point where the function f of x has all this continuity right there. So now that point is the breaking point between the two for the two pieces of improper integrals. Okay, and so now I'm looking at with this one here. Yes, a little substitution like I've said, like how I have done before, u equals x minus 1. And so we have seen that in the earlier part of this same problem. So how about allow me to skip the major part of the work, but u1, when t equals 1, it's going to be, u1 is t minus 1. When we substitute t into the u substitution pointer here, so t minus 1 equals u. That's the lower end of our integral. And so that's what I'm putting in for the next time. For the next step right here, u2 is 9 minus 1, which gives me 8. So now this is what my integral becomes. So very similar to the work I've done for the earlier integral. So here it's t minus 1 to 8. All right, and then the integral now becomes 1 over cube root of u because I substitute u away. And so all that similar arguments up, you can refer back to the earlier part of this example right there. And now it's du, okay, and we want to take the limit as t approaching 1 from the right endpoint, from the right hand side. All right, so now all of this here can be gone. So now in my next step, I'm looking at, and just again see this as u to the negative 1/3 power. And so now the power rule says we can take the antiderivative of that, and which gives us here u to the positive 2/3 multiplied with 3/2. Okay, and then we're gonna evaluate that from t minus 1 to 8 right there. All right, and then yes, that is a limits problem where we're letting t approaching 1 from the right endpoint. Okay, so now that means I'm going to go ahead and proceed further with the fundamental theorem of calculus here. I'm going to evaluate the low and the high into the antiderivative. So 3/2 times 8 to the 2/3. Okay, and minus, I'm going to subtract 3/2 times t minus 1 to the 2/3 power. All right, and then overall, now we realize that this is an expression in terms of t. I'm going to go ahead and apply the limit operation by letting t approaching positive 1 from the right hand side. Okay, and so just a brief calculation, h to the 2/3 power is going to be a 4, but 4 cancel with that 2. Is another 2 left behind, so 2 times 3 is a 6 right here. So we're looking at, it's a limit problem of 6, t go to 1 from the right hand side, but that first term becomes a 6. Now minus 3/2 times t minus 1 to the 2/3 power. Okay, but now as we're taking the limit of this work right here, that second term goes to the 0. All right, it goes to a 0, and this first term remain a 6 right there. So in the end, my answer now for this, it's a finite value now. All of a sudden we realize it's a finite value. So here it's 6 for that overall the limit right there. So now that means this integral here, this improper integral is convergent and it's equal 6. So I'm going a little, because we're not focusing on this problem only, it's only part of our bigger work. So I'm just going to get straight into saying this answer here equals 6. Okay, and so now that means I can go back and make notes here that this answer is that answer there turned out to be a finite value, 6. And now we can, the definition says if both of these improper integrals are finite, and that's the case here, or are convergence, which will give us eventually finite values, which is the case here, then this answer here, this integral here, first thing, is a convergent. So now I'm going to say it I'm going to conclude that on the other board. All right, so much writing, but I have to erase that almost immediately. All right, so that means as a conclusion, first of all, we're concluding that 0 to 9, the improper integral from 0 to 9 on cube root of 1 over cube root of x minus 1. This integral is convergence. Okay, convergence. That's one. That's the first thing we already decided. We have already determined. And now furthermore, now that I'm looking, this actual improper integral can be evaluated, okay, by minus 3/2 is the first one that we broke it down. So this is the one, that's a negative 3/2, and then we're going to add that. Now we have all our legal right to add that to the final finite numerical answer for the other one, being 6. Okay, so now it's going to be a minus 3/2 plus 6. Okay, so the final answer now comes out after the simple math here is going to be a 9/2. Okay? And that is now our final answer. So we've done 2 work. One work is simply just to determine if it's divergent or convergent. And we said that it's convergent here. We decided it's convergent here. A lot of work. Okay, but once it's convergent, then the last step is to make that final evaluation. It's a lot simpler because any of these supposed to come in the previous step, part of the work where we deciding convergent or divergent already. So now just simply adding up the 2 answers here, that gets us the final answer for that. Okay, so now this integral is a convergent one, and it converges to the value 9/2. Okay, so that's how I see that with this particular example. All right, and so now at this point, after looking at the examples 4 and 5, we have come to the following generalization. So as far as those improper integrals that we have seen throughout example 4 and 5, those integrals on some function f of x with the integration interval from a to b. One case we had was the function. One case we had in part A, in case A right here, was to describe the case where the function f of x itself has a discontinuity at x equals a. And then in another case that we have seen, case B, and I might be a little bit out of order compared to the lecture that we have seen previously, but again, suppose we're looking at an integral from a to b. But the integral here, the improper integral here, is in a situation where the function f of x itself has a discontinuity at x equals b, the upper limits of our integration interval. And so the 2 cases here both reflect a common characteristic, that we have our function in both of these 2 cases. We have f of x has a discontinuity and this is worth to be highlighted, to be underlined. So f of x has a discontinuity in the integration interval. All right, and that's the one common characteristic throughout the 2 cases A and B that we have investigated throughout the examples 4 and 5. And further, we came to the final case where, again, at first sight, the integral looks just as usual as any other ordinary integral. But this integral could be an improper integral in the sense that f of x has a discontinuity. Allow me to use a shorthand writing here. It's short for discontinuity. So in our case here, f of x, in this case C right here, f of x has a discontinuity at some value x. At some value x equals c, that's inside, and more importantly, it's that value c is some value c being inside of the interval or inside somewhere between inside of the interval from a to b, which is our integration interval. And so this is also the third case, which is the more generalized case where it describes the fact that f of x has a discontinuity in the integration interval. And so improper integrals, or any improper integrals of this kind, is being referred to as the improper integrals of type 2. So in other words, those improper integrals that we were seeing throughout example 4 and 5, a lot of times we refer to those as the improper integrals of type 2. All right, and so now after we have successfully classified what it means by being an improper integral of type 1 and what it means by being an improper integral of type 2. Now, I would like to acknowledge the fact that everything we've learned here at the Calculus 2 level is only a very limited understanding of the real world of improper integrals out there. Okay, so of course, but the more advanced and the more complicated kind of problems we'll have to wait for when you arrive at a more advanced course in mathematical analysis. Okay, but now before we conclude our complete lecture here about all the improper integrals that we're learning here, I would like to bring up an example that kind of combines everything we've learned since the beginning of our lecture here, including an example that including all of the improper integral type 1 and with some improper integrals type 2 right here. But I specifically brought up this example in the purpose so that you get comfortable to the way of how it's worded as well. Okay, and so now allow me to get into example 6 right here. So now we're at example 6. But now the wording, the instruction of the problem, now it's saying that evaluate, okay, and evaluate. And now allow me to immediately write down the first problem. And so aside from getting to know the kind of wording of the example, which is the kind of wording of the problem here, instead of, like the earlier example, it says first we have to determine whether an integral is convergent or divergent. And then once it's convergent, then we evaluate it. And here just a one simple term. That's how it's also, that's how some common problems out there about the improper integrals will happen out there. The instruction of the problem just say abstractly evaluate an integral. And so and I will get more into explaining what that term, what the wording here of the problem means. But now aside from presenting the different styles of wording in this problem right here, I would like to also emphasize the fact that I would like to bring up different problems so that you get better experience of identifying what kind and what type of improper integral that is. Okay, and mainly for our class that we learn here, there are two types. Type 1 is the one that involving the improper integrals, all of those improper integrals that have the infinite interval. Okay, and then type 2 that we learned prior to this, example 6 right here, are all those improper integrals that have an interval with discontinuity inside somewhere of that integral. Somewhere of that interval of integration. Okay, so now let's first write down the problem right here. So I have the function here is 9 over x plus 5 to the 3/2 power. But now I want to take the integral from 2 to positive infinity. Okay. All right, and now as far as getting yourself comfortable with identifying the integral, then this is an integral, this is an improper integral, clearly speaking, but then it's also the interval of integration is involving the positive infinity. So that means we're now looking at a type 1 improper integral. So it's just a note, but nobody is requiring you to indicate this is a type 1 every single time. It's just knowing it's a type 1 or type 2 will drive you into the proper solution right there. That's all there is. So here I'm only making a note for anyone viewing the lesson here to be acknowledged about, but really you're not required to indicate that your problem is a type 1 or a type 2. At least not for students who are studying directly with me for calculus 2. But now, aside from being able to identify the problem given to you here, you see, if you're looking back at, I now would like to clarify why a problem like this is asking you to simply get straight into evaluating. Because, I mean, improper integral, any improper integral problem is a no joke thing. I mean, I purposely walked you through 5 examples prior to this one, and any one of them is all started out by you first have to decide or determine whether your integral, your improper integral, of course, is convergent or divergent before you can evaluate. Because if it's divergent, then we're going to stop the problem and saying, hey, the integral is divergent without worrying about evaluating. But we only evaluate once we knew. We can only do that. We can only evaluate once we knew the integral convergent is convergent. The improper integral is convergent. And that's the kind of intention I would like to point out here. So for your experience, anytime that you are given a problem that you are about to work with an improper integral, and the problem, the instruction of the problem in words saying just evaluate, there's a hidden intention behind the scenes. There's a little clue that was not specifically mentioned, but that clue there is that we kind of know in the back of our mind that this integral will converge. That's what I'm trying to express right there. So when your problem is asking you to evaluate, that means the author, whoever gave you the problem, already had an intention. They gave you, the author of the problem gave you a problem to work where it was already known somewhere to be a convergent one. Okay, so really in your process here, you just simply need to carry through the process of proving the limits to converge, and meaning you go to a value and then concluding that this integral will equal to that final limit. Okay, and so of course you can watch through my steps here, and then you will get a better understanding of what I've been saying the whole time about this example. Okay, so now I know in the back of my mind that this problem will converge, this improper integral will converge. So in that way, now I can kind of illegally, I mean it's not too formal, but I can informally say that it's equal to, because we can kind of put ourselves in that assumption that it's the limits from 2 to t, an arbitrary t value, but letting t to infinity. We can kind of assume that this is equal, because like I said, in the back of the mind, the intention here is that we are really given an integral that's known to be convergent, but someone done that here, which is kind of doing it the second time to make it clear. Okay, and so now I'm producing that limit, but now we are legally allowed to set that equal sign. This improper integral equal this limit. And then, of course, the function is 9 over x plus 5 to the 3/2. Okay, and so now we can just keep proceeding. So now once we see that if it's convergent, and if we are asked to evaluate, then we know in the back of our mind it should be convergent, so we can set that equal to this. And so from this point on, we can keep working through the limits problem. Okay, and that's the whole different style of the two problems right here between this kind of problem and those kind of problem that I really want to get you guys, anyone learning through calculus, comfortable with throughout all examples from example 1 to 5 right there. Okay, and so now here it is going to be a limit problem, of course, letting t to infinity. Okay, but now I'm going to do a little bit of a u substitution. So actually, how about and so now let me do a little substitution here. I'm going to substitute for x plus 5. Okay, and so that means du dx is going to equal 1, and that means our du equals dx. So this will later on become a good substitution for our dx expression in the current integral here. Now my low limits in respect to the u variable, so I call it u1, is going to be 2 plus 5, because 2 previously is now substituted for the u expression, so 2 plus 5 equals 7, and then my u2 previously in terms of the x variable, and then we substitute t for that, but here it's going to be t plus 5. Okay, and so now with this work right here, now I'm ready for really making the variable change, the substitution completely right here. So it's a limit problem, of course, as I'm letting t approaching positive infinity. Now low limit becomes a 7, up limit is a t plus 5. Okay, the 9 did not get a substitution, so I'm leaving it there. X plus 5 is now substituted by a u, so my expression has become significantly shortened. So it's u to the 3/2 power. Okay, and then dx is substituted by a du. So that's how the problem becomes. And so once again, we notice that 9 over u to the 3/2 power is the same as 9 times a u to the minus 3/2. So that gives us a hint or a clue about how to move on when in our step finding the antiderivative. Okay, and so after this point, and at this point, after you have seen tons of example problems, and allow me to start speeding up the steps a little bit. So for my antiderivative of 9 over u to the 3/2 power, so realizing that to be a 9 times u to the negative 3/2, then my antiderivative turns out to be 9 times, so now u to the negative 1/2, because negative 3/2 plus 1 is a negative 1/2, so negative 1/2, but I'm dividing that by a negative 1/2, so that means we're multiplying 9 with a negative 2. Okay, or in other words, 9 times a negative 2 times u to the negative 1/2 power. Okay, and we are now going to evaluate this antiderivative in terms of u from 7 to t plus 5. Okay, and then of course this is going to be a limits problem allowing t approaching positive infinity. Okay, and so now this is going to be an overall negative 18 coefficient, and u to the negative 1/2 is the same as, okay, so it's minus 18 over square root of u. That's how I'm seeing this, the final antiderivative as a square root expression. And then we will eventually substitute in 7 and t plus 5 for our expression. And then yes, this is in the end, of course, a limit problem as we're allowing limits to infinity. So, and everything here, I'm strictly going through the fundamental theorem of calculus, because in the end, at this step right here, when we're setting that arbitrary t so that we can have an integral from 2 to t, then this is entirely aside from the limit notation, then this is entirely a definite integral. So everything I'm doing here aside from the limit symbol is to follow the work of the fundamental theorem of calculus. And then so now I am going to substitute the two integral limits here into my expression. So what I'm looking at now is that I'm having minus 18 divided by square root of t plus 5. Okay. And then I'm going to subtract, and then now I'm going to have negative 18 over square root of 7. Okay. And then now this current expression here is entirely now in terms of t, and so it makes it consistent with our work here that we desire to take limits as we let t approach positive infinity. Okay, and so this last term here is due to the double minus sign here, minus negative, so it's going to become and it's a constant term, so it's become a positive 18 over square root 7. But the first term here, okay, the first term here is a minus 18 divided by square root of t plus 5. And we're taking limits as t go to positive infinity. So now with this final expression, we are very ready to find that overall limit. Now, this first term here, we have a constant divided by a growing quantity. So we've learned that all over our calculus 1, that when we run into a situation like that, the overall limit will become a 0, because the denominator will keep growing large where the numerator stays constant. So the first term is 0, and that means our final answer here is 0 plus 18 over square root 7. My final answer is 18 over square root 7. Okay, so here's the logic again. You see, so this work here is not only showing us that the limit work turns into a convergent one and showing the integral is convergent, but further than that, it shows, so that's why, like I said in the beginning, it's already intentionally kind of tells you implicitly that the problem will be convergent. So all we do is just set that limit, set that improper integral to equal this limit, and whatever the answer here, it's not only the answer to the limit problem, but it's also the answer to that integral work. And so now with a problem like this, then we are legal, it's legal for us here to put that in a box here and say this is our answer to the improper integral from the beginning. Okay, so it's kind of less steps for us because somebody, whoever the author gave us the problem, whoever the author that is who gave us the problem, he already intended behind the scene that the problem will be a convergent one. So all we have to do is set that problem. So watch out for that style of the wording. Anytime it's asked, it gives you an improper integral and then asks you to evaluate. That means it's already kind of known to be the convergent. So all you have to do is just to make it clear. So right from the beginning step, you can freely set that equal to the limit and then do your work, and then at the end your final answer for the limits will be a value, and then that value will be the answer to this improper integral. And that's what my point is. Okay, and so now in that way, now we're gonna start flying and start picking up speed and pace into the later problems like that. Let's call that now part B. All right, so let's call that now part B of our problem right here. So what about an integral as following, from minus infinity to infinity? Okay, it's an improper integral on the function 1 over 1 plus x squared. Okay, 1 over 1 plus x squared. And so it is, again, just make a note for yourself. You don't have to indicate that. It's not a requirement unless your teacher really wants, but at least for students who are studying with me, you don't have to. All you do is realize clearly that your problem here is an improper integral type 1 again, because see, the interval here is completely an infinite interval. Okay, the interval where we're integrating over. So it's a type 1. Okay, but now, and again, the problem we're given a new integral problem, but it's under that categories. Again, the author, it could be me here in this problem, the author already gave you a problem where intentionally it was meant to be a convergent one already. Okay, so now in that way, keeping that in mind right there, then we can get straight into, but it's a even though it's type 1, but it's the sort of like the comprehensive one, the one that we have to break it up. Okay, recall that. So if you're not sure what I'm talking about, roll back to the part of the lecture where I was going over this kind of a problem like that. So that means here I can pick a value. Now, technically you can pick any value, and you see this function here is a continuous function. It's a continuous function, except for we just don't have a finite limit and we don't have a finite upper limit. Okay, and so I'm for simplicity, and by the way, 1 over 1 plus x squared function is this, graphically speaking, it's this shape right here, and it's an even function. So and the interval here looks pretty symmetric. Even though we don't know the two definite ends, but we have our right to call that, we can have our right to treat 0 here, even though you can also pick 1. You can pick 1, you can pick -1, you can pick -2 or -half. I tend to pick 0. It's just me. I want to reserve that symmetric nature of this function right here. Okay, so with so much talking, this is what I mean right here. So 0 is somewhere in between -infinity and infinity. So I'm going to produce one problem that's accumulating from minus infinity to 0. Okay, on this function 1 over 1 plus x squared. Okay, and plus the problem from 0, accumulating from 0 to positive infinity on the same function 1 over 1 plus x squared. And now, so we can, for a problem like this, where we know in the back of our mind that it will be a convergent one, then we can legally set that equal to the sum of these two. because we know that these two will give us convergent ones. Okay, and so, but now in the end, when we're setting it up like this, we're still going to have to tear it down into two separate works, because we don't want to deal with something like this, two problems in every single one step. It's going to make things a lot of work for us to keep track. So how about I'm going to kind of branch out and work separately on minus infinity to 0 on that function, 1 plus x squared. Okay, so that means for this function right here, I am going to call that, I'm going to call an arbitrary t variable, okay, to 0 right here. So that's making it an ordinary definite integral right there. And then we're going from 1 over 1 plus x squared, and we're integrating from t to 0, taking that limit as t going to positive infinity. Okay, and so now this function is simple enough that you can see it's just out of what we remember from calculus 1. Tangent inverse, the derivative of tangent inverse will give us 1 over 1 plus x squared. So now taking the antiderivative as part of our work right here in integral, then this is going to be the antiderivative for this function is tangent inverse of x. Okay, and then according to the fundamental theorem of calculus, I am going to evaluate it from t to 0. Okay, and of course this problem will eventually at the end be a limit problem where we're letting t approaching positive infinity. And actually I need to correct myself. This is here minus infinity actually. We're letting t approaching minus infinity. All right, and so now in that way, how I'm seeing this, okay, it's tangent according to the fundamental theorem of calculus. We're going to substitute 0 for tangent inverse. So tangent inverse of 0 minus tangent inverse of t. Okay, and then yes, now at this point we have arrived at an expression that that depends on the variable t right here. So we want to find out what will be the limit here if we're letting t, what's our limit of the function as we're letting t approach negative infinity. Okay, and so now for this, you can see that tangent inverse of 0 is a 0. Okay, tangent inverse of 0 is a 0. And then this tangent inverse of negative 1. So allow me to explain in a different various case right here depending on the situation. But how about this time, let me bring up the graph right here. Okay, and so here's our decimals of my graphing calculator on decimals right here. And tangent inverse. All right, here we go. Tangent inverse. And now let me zoom it out right there. Okay, so tangent inverse is asymptotic. But I mean, this is the graph for tangent inverse. So, all right, that upper line in red I have just put on there on my, that's when t is going to positive infinity. When t is going to positive infinity, then tangent inverse will have a horizontal asymptote at pi over 2 right here. So this is y equals pi over 2. And then the same way when we're looking at y equals minus pi over 2. Okay, so these are all understanding that we need to know from our pre-calculus courses here. But minus pi over 2 is the other horizontal asymptote when we're letting t approach, or we're letting x approach negative infinity, which is our case right here. So now in our case, back in the problem, we're looking for taking the variable of the function to negative infinity. So now this part right here, just a tangent inverse on t, it will approach negative pi over 2, but with a minus sign here. And so now from that understanding, then I'm looking at in the next step, okay, it gives me a 0 minus a negative pi over 2. So this is a positive pi over 2. But it's only half of our work here. It's only the answer to that. And like I said, right from the beginning, we already had for ourselves a goal. We kind of knew in the back of our mind that this will converge. That means no matter how we're breaking it up, somebody can choose a 1 here. Somebody can choose a negative 1 here, or a negative 5, or negative whatever, or 1,000. But any of these broken up parts has to be a convergent one. just like how I used 0 here. You can use 1,000 there and 1,000 here, okay? But any one of your broken up parts has to be a convergent one. So here it converges to pi over 2, okay? And so now I'm going to navigate to the other board and continue the other work, the work on this problem right here. All right. And so now, for that integral from 0 to positive infinity of the same function, 1 over 1 plus x squared, okay, I am going to set that up as equal to the limits, as I'm letting t to positive infinity. And then now we're going to set from 0 to t. So I'm using again. Now this t here, in case I haven't clarified in my earlier problem, but this t is not necessarily the same t. It's not necessarily the same exact t as this t. It's just some external variable that we use temporarily, okay, to set up our limit problem right there. So they're not necessarily the same t. And that's why I'm trying to encourage people not to do these two problems, the two separate improper integrals in the same step right there, because it could be dangerous. You're using the same t and it's caused a serious misleading. Okay, and so now it's a separate problem here, 1 over 1 plus x squared. Okay, and so now that gives me that function again, antiderivative is going to be tangent inverse of x. Okay, I will need to evaluate this from 0 to t. All right, and then I'm going to take this as a limit, allowing t to approach a positive infinity. Okay, and so now again in the next step, fundamental theorem of calculus is going to happen here again. Tangent inverse of t minus tangent inverse of 0 according to the fundamental theorem of calculus. And I'm going to let t approach a positive infinity. And then very similar to the work we have done earlier, this tangent inverse of 0 is going to give me a 0, and it's a constant. Okay, and then the tangent inverse, I've demonstrated on the graph, and now I can swing back on the computer screen and pull out the graph again. And so here it is, our graph. But this time for tangent inverse, and so the horizontal axis now is, let's call it, it's a t-axis. But as we are letting t approaching positive infinity, meaning I will keep tracing out further and tracing out further to the right hand side on this graph, then the graph itself vertically will approach a positive pi over 2, this red dotted line right here. All right, so in that case, right here, this tangent inverse of t, as we're taking limits, it's going to become positive pi over 2 and minus 0. So our final answer for that is a pi over 2. So now we've had the two pieces of work right here. Okay, so now I am going back to my board, to this board here, and erase out some steps. Let's take note that this piece of improper integral, gave us a pi over 2. This improper integral gave us another pi over 2. And so now I can erase this. Okay. And so now, legally speaking, after so much work and tearing things apart, now continuing with this step right here, this improper integral gives me a pi over 2. That's still noted here. And that's what I did on purpose, so that I can still have something to recall myself, to remind myself. And then the work for this improper integral is from the other board, being another pi over 2 here. All right. So now that means I'm going to add with another pi over 2. And like I said, we've been constantly keeping in the back of our mind that right at the instant this problem was given to us, in the way how it's worded, we already knew that it will converge. It's just now we're going to really go through the limits work to find the limit value right there. Okay, so now it's a pi over 2 plus a pi over 2. Our final answer here is a pi. And that's how we have evaluated this particular problem. Okay, so it's a lot easier than the kind of problem where we have to decide whether it's convergent or divergent. And then only if it's convergent, then we will evaluate. Otherwise, if it's divergent, then we're going to stop at the divergent one. So it's slightly different logic. Okay, different logic. Here we already route ourselves into that that direction where we already knew it will be convergent. It's just we're going to have to keep going further and evaluating the final limits. Okay, and so now let's look at part C. So the first two problems was all about the in-depth, was all about the infinite interval, but it's all about how we realize our problems. And this example 6 is supposedly to create a mix of problems, of improper integral problems. So part C, I'm not going to say too much about that yet. How about integral from -1 to 0? Okay, and our function here is e to the 1 over x cubed. All right. As right at first sight right here, the function looks just like any, the integral looks just like any other ordinary definite integral. But now if we're looking a little further, x equals 0 is critical for both numerator and denominator. Okay, so that means this function here is this integral here, this improper integral here is a type 2. It's a type 2 where we have a discontinuity at the upper end, right there, the upper limit of our integral problem. Okay, so but like I said, at least for me, whoever studying calculus 2 with me, I'm not requiring you to do this. Okay, but do watch out if in case you're only viewing my video here and learning that with somebody else right there, then watch out for your instructors to see if he or she requires you to indicate whether it's a type 1 or type 2. Okay, but all I expect here for students who study with me is to know your kind, so that your kind of improper integral, so that you will drive into the correct solution. Okay, so now knowing the fact that it will be a convergent one, like I said, that's the problem right here. And so now I'm going to set up a limit, an integral from -1 to t right here. Okay, because the upper limit here is the critical one. And so I'm going to use an arbitrary t where t is less than 0. But now I'm going to let limits of t goes to the upper limits there, but from the left-hand side. Okay, and now we're doing e to the 1 over x cubed. Okay, and that's the limit setup that we're doing. And so now, in that way, here's my next step right here. So now once we have successfully set up the limits problem right there, then aside from the limits, then this integral is entirely an ordinary definite integral. And so now I can go ahead and proceed just like a definite integral. So here I'm doing that. I am going to let u equal 1 over x. Okay, and so that means my du dx will equals -1 over x squared. Okay, -1 over x squared. And then that means further that my du over, or I can just rearrange this as minus x squared over du, minus x squared times du equal dx. Okay, that will create for me a later substitution point right there. And then I will, so my u1, when x equals -1, then u1 will equals -1. When x equals t, then u2 will equals 1 over t. 1 over t. And so now, well, let me write the 1 over t down here. So u2 equals equals 1 over t. All right. And so now I'm ready for the work right here. It's a limit problem letting t approach 0 from the left-hand side. here I'm looking at negative 1, okay, to 1 over t, and here it's my function becomes a e to the u, because 1 over x right here has been substituted for u, so it's e to the u over, now x cubed did not get a substitution, let it be that way, but dx here can be substituted now by minus x squared over minus x squared times times du, so minus x squared times du. And so now I can recognize I can cancel the x squared away and bring the minus sign in front, and then cancel that, and that leaves me an x right here. So in my next step, it's a limit problem, okay, for t to 0 from the left hand side of the negative integral from minus 1 to 1 over t of e to the u times 1 over x. I purposely wrote it like that, du. But see, hey, observe this, 1 over x is another, 1 over x here is another u. It's the art of substitution. It's, the word for doing substitution problem is such a limitless world out there, okay? And you have so many ways to be creative. And then that's why I said there's no right or wrong in how you choose your substitution. So that means your problem in the end becomes t go to 0 from the left hand side minus integral of from negative 1 to 1 over t, but it's u times e to the u du. Okay. All right, and I will be navigating over to my other board right there for the next step. All right, and so now allow me to rewrite the step from the previous work. Okay, so at this point from our most current step from the other board right there, allow me to rewrite it. So it's limit as we're letting t approach 0 from the left hand side on our current integral, and so it's minus, and the integral is from minus 1 to 1 over t times u times e to the u du. Okay, so with this particular antiderivative right here, we can use integration by parts. Okay, and so in case that anyone is not sure, I can briefly remind about the work for integration by part on that particular function. Let's say separately branched out a little bit here. How about x times e to the x dx on this particular function? And if any of the step here is going too skippy for you, then I recommend finding my video lesson that I teach about how to do the integration by parts. But so I see a polynomial over here, which is an algebraic family, and I see an exponential family right here. So my u choice, to break that into the two parts, my u choice here, I'm gonna call that the x, and my dv part is e to the x dx. But of course, I'm going quite skippy here because this is not formally a lesson about the integration by parts. And so now if u equals x, then du is going to equal dx, and on the other hand, now if dv equals e to the x dx, then v can equal e to the x. And so this integral will become, now so the formula for integration by parts says we need to multiply u with v. So it's x times e to the x, and I'm subtracting an extra integral that goes from now v with du, so it's e to the x dx. So that means in my next step, the integral becomes, so first term x e to the x and minus, now that's simply just e to the x. And we don't need the plus c here because this is just part of our definite integral work. So now when our function is u times e to the u, then now I'm ready for the next step. So it's going to be now u times e to the u, okay, minus e to the u, and I'm going to go ahead and evaluate this from negative 1 to 1 over t, okay, but it's, don't forget we have a minus sign in front like that, okay, and then this problem will become a limit problem at the very last step where we're letting t approaching 0 from the left-hand side. But now it's supposed to be another step after this, but allow me to just think about in the next step, I'm going to spend one more step to distribute this negative sign to each term, but allow me to fix that right from here. So that means I'm looking at a positive e to the u and minus u to the e to the u. Okay, so that's my antiderivative for that function. And now we're on our way to apply the fundamental theorem of calculus to substitute these two integral limits into our function. So this is what I'm going to get in the next step right here. So I'm looking at, how about I need a little more space here. So e to the 1 over t minus 1 over t times e to the 1 over t. That's how I substitute 1 over t expression into my antiderivative here. And then I'm going to subtract. And now I'm going to use a quite massive amount of parentheses here. So e to the negative 1 power, or I can just for short write that. To the negative 1 minus, but now negative 1 times e to the negative 1. All right. And then realize that all that here will be a constant term. Okay. And I'll just briefly remind about that. And so let's find out what that limit is. So limits as t approaches 0 from the left-hand side. T approaches 0 from the left-hand side. Okay. And so now, so everything we worry about is mainly this, the limits here, because that's the only term that has t involved, and that's changing depending on the value of t right there. Everything else is going to be a constant. So I can quickly explain, and you can always utilize your understanding from calculus 1, but think about the t variable here. If as t is getting close to 0 from the left-hand side, then it means 1 over t will get to limits. I'm just talking about this particular part right there. So 1 over t will become negative infinity. Okay, but so that means if e here is raised to a quantity that's go to negative infinity, then the overall, this overall limits right here will come down to a 0. Okay, now allow me to use my experience here, and I will branch out at the end of the problem here to explain how, but this particular limit right here as well, as t go to 0, from the left-hand side, and this limit will also go to a 0. And like I said, put a star here, so I will come back and explain why that is. Okay, but now sweet, in the end, both of these two terms, as we're letting t approach 0 from the left-hand side, both of these terms go to 0. So that means we have everything left behind with this constant term right here. So that means now we're done with the limits work. We're looking at minus. Now I'm distributing this minus sign to each term right here, and the first term here I'm writing that as a 1 over e, because e to the negative 1, that's what it is. And then so minus, negative, and negative, so it's become a minus another 1 over e. So my final answer is, shockingly, minus 2 over e. Okay, and this is really the answer. So now, as I've been explaining, this is really the answer to our improper integral of type 2 right here. And as I said, the way how the wording of the problem is indicating it, that we kind of knew ahead of time already that this integral will have an answer. Okay, this integral will have an answer. But so that's why we can set it up and then just go ahead and proceed all the way to the final successful limit, and our final answer here turned out to be a finite value of minus 2 over e. Okay. And so now, before I'm closing down completely on this problem right here, allow me to explain why this problem right here. Let me now put a circle there. Allow me to quickly explain as a separate problem in case anybody wonder. Okay, so let me just side out and explain about why this 1 over t times e to the 1 over t here will go to 0. Okay. So now we're done with the big problem in part C, but let me give a one piece of explanation right here that will fill in the gap for you. So mainly, let's consider this problem separately. The problem we had there was in the form of we're letting x go to how about 0 from the left-hand side of the function was 1 over x times e to the 1 over x. Okay, it's that kind of function. So think about, you can use a temporary u right here. I'm going to substitute u to equal 1 over x. I'm going to let u equal 1 over x. Okay, so if think about it, the 1 over x function is having graph as following, and anybody at this calculus 2 level knows the graph for 1 over x function. This is 1 over x. So now if u is equal to 1 over x, and we're particularly approaching 0 on the x-axis, approaching 0 from the left-hand side, then 1 over x is going to drop down. So that means u will tend to limits. U will approach, see, negative infinity. Okay, negative infinity. So that means the problem here has a better form of writing it. The problem has a better form of writing it that this same exact limit problem can be rewritten as a limit, where I'm treating that as a brand new variable, u approaching negative infinity, for the function u times e to the u. U times e to the u. And now I taught at least for my class when I was teaching calculus 1 back then, I highly recommend this method right here. Anytime that we are working with a limit to infinity, to negative infinity specifically, then I'm using another substitution. How about let the main variable here to equal a minus z. A minus z. But then if u equals minus z, then that means z will approach positive infinity as our u currently approaching negative infinity. This is the part where you can pause the video and double check for yourself for me to agree with me right there. Okay, and allow me to not to get too far into that basic explanation. But now it gives us an advantage, because now let me erase this. Once I'm doing this, then the problem becomes so let me just make that note right here. I'm letting u equals negative z. So the problem, so one more variable change right here. So limit by letting z approach positive infinity, but it's a minus z times e to the minus z right there. Okay, minus z times 1 times e to the minus z. So that means this expression here is the same as a minus z over e to the z. And we're letting z approach a positive infinity. And so here we can apply the L'Hopital's rule. And L'Hopital's rule is taught at usually the calculus 1 level. So if you haven't if you haven't had any experience with L'Hopital's rule, find my video lesson for my calculus 1 course where I was specifically teaching about the L'Hopital's rule. But so now this limit here is essentially the indeterminate form infinity over infinity. Well, it's really negative infinity over infinity. We can put that we can put that negative sign in front. So essentially this overall one is infinity over infinity. And so now when we're in that indeterminate form, then I can just take the derivative of z and take the derivative of the other e to the z separately. So two separate derivatives. Okay, but like I said, allow me not to go too far back at ultra basics of any of these limit stuff right here. So L'Hopital's rule, according to L'Hopital's rule, okay, we will have the limit. This limit will equal to limits of negative 1, because derivative of z in respect to z variable is negative 1. Derivative of e to the z in respect to z is e to the z. Again, okay, so now with this final limit here, then this limit here is apparently going to 0 clearly. So that means this limits go to 0. That means that limits go to 0, and that limits also go to 0. And so consequently, the whole imply that the whole 1 over x, e to the 1 over x, by letting x approaching 0 from the left-hand side, that will go to 0 as well. Okay, that's our quick little branched out proof of how I was doing that 1 over t times e to the 1 over t, letting t go to 0 from the left-hand side, approach 0. Okay. All right, and now let's look at another one in this example 6 right here. And I believe after this one, it should be enough to cover to cover a lot of experience for any of my students to learn through this concept of improper integral right here. Okay, so what about, let's look at another one here. How about we have an integral in part D here of our example 6. We are looking at integral from 0 to 6, okay, of our function 1 over x minus 4 raised to the 2/3 power, okay, 2/3 power. X minus 4 raised to the 2/3 power. Okay, so now as I said again, the problem is asking us to evaluate, and it gives us here an improper integral. Now, let's identify the kind of improper integral, even though I will never require my students to specifically indicate what kind of what kind of improper integral that is. But it's good to know it so that we can come up with the correct plan for it. So the improper integral here, it seems like it has definite integral interval here, but it's not, because you see when x equals 4, which is a value somewhere between 0 and 6, and we will have a discontinuity for this function at x equals 4, and so please don't just find antiderivative of that and substitute the x equals 6 into the antiderivative and x equals 0 into the antiderivative. I've spent a lot of time, I believe, to explain how dangerous that is. So here we have to really realize that it's an improper integral of type 2, and the worst thing is that it has, this function f of x, right? This is our f of x right here. As a quick note right here, f of x has discontinuity. Okay, it has discontinuity at x equals 4, which is inside of the interval from 0 to 6. Okay, that's what we need to realize, and that's making it. This is a type 2 that we previously learned through the formal lecture earlier. Through the general lecture discussion. And so now, knowing that it's a type 2, but now again, it's already meant or intended to be a convergence integral. And so that means, and I pointed out that we realize there is a discontinuity at x equals 4 between this. So that means we're going to tackle down right on that point. I'm going to produce this, I'm going to proceed with this kind of known convergence integral as an integral from 0 to 4. So this is the discontinuity point right there on the function 1 over x minus 4 to the 2/3 power. Okay, and then I'm going to need to add that with another separate improper integral from 4 to 6 right here. Same function, 1 over x minus 4 to the 2/3 power. All right, and now we can. And once we have that starting setup laid down right there, and like I said, because the problem kind of expects that the improper integral will become convergent, that's why it is completely legal to set this integral equal to the two pieces of integrals right here. But then now in the end, we still need to kind of slow it down and work on each problem here as one separate improper integral on its own right here. So allow me to get started with the first one here on the left. The first one here on the right hand side of the equal sign, but on the left of this sum. Okay, so now I'm looking at 0 to 4, 1 over x minus 4 to the 2/3 power. I'm going to think of that as, and knowing this one here will be convergent too, simply because if this one here is intended to be a convergent, then both of these must be convergent. Okay, both of those must be convergent. And so in that way, knowing that this should be convergent, and so we can also legally equate that with the limit that I'm letting t approaching 4 from the left hand side, and here I'm going from 0 to t, and my function here is 1 over x minus 4 to the 2/3 power. All right, and that's how it happens right there. And so now in that way, now I'm going to go ahead and proceed as usual. Well, I'm going to use a little bit of substitution. I'm going to substitute u equals x minus 4 So that means du dx should equals 1, and that leads to du has to equals dx. So that's eventually become a substitution point for us here. My u1, when I substitute x equals 0 into this expression x minus 4 right here, then that's how I get u1. So u1 will equal minus 4. Okay, so 0 minus 4 equals negative 4. Now u2 is found when I substitute my upper limit here t into the u substitution. So it's gonna, so u2 consequently turn out to be t minus 4. All right, and so now with all that information, here's how my integral will become. So I'm looking at an integral from minus 4 to t minus 4, and 1 over, now all of that there is shockingly u to the 2/3 power. All right, and all I need now is to substitute dx with my du expression, because that's what we found for it. Dx is substituted by du. And so I'm substituting that here, and the problem becomes, the problem still remains a limit problem where we're letting t approaching 4 from the left hand side. Okay, so that's how I clean up my terms a little bit here. Allow me to rewrite this so make it look a little more neat right here. 1 over u to the 2/3 power, okay, and then with the du. All right, and so now with all of this, now I can clear out all of this scratch work for the substitution for here. All right, so now in my next step, I'm going to go ahead and apply my fundamental theorem of calculus, because simply, again, aside from the limit problem right here, then this problem now is an ordinary definite integral where we go from minus 4 to an arbitrary t minus 4 on that function in terms of u. And so, again, we are seeing this 1 over u to the 2/3 as a u to the minus, okay? This is the same as u to the minus 2/3 power, okay? And so in that way, now I'm going to write that as, now the antiderivative here is going to become u to the, now minus 2/3 plus 1 is going to be giving me a positive 1/3, okay? And then I'm going to divide that by the new power, so that means it's going to give me 3. All right, and now with that antiderivative, I am going to eventually evaluate that from minus 4 to t minus 4 right there. And I'm taking the limit as t approaching 4 from the left hand side. Okay, and that's it. So it keeps turning out with some good direction of where to go next right there. So now I'm going to continue with my fundamental theorem of calculus, substituting t minus 4 into my expression there. So it gives me 3 times t minus 4 to the 1/3 power, and there's no need to write this as a cube root. It depends on the situation, but here we don't have to. And minus, and now 3 times negative 4 to the 1/3 power, and all that here. Now everyone realize clearly that this is an expression in terms of t. That is a constant term, okay? And now I'm looking at taking the limit as t approaching 4 from the left hand side. All right, so now it is clear that as, and this is the only term that's dependent on t right here. So now as t is getting closer to 4 from the left hand side, and this whole term go to 0. So I have a 0 there, and then minus. So now it's and negative 4 in the cube root. So that's making it we can bring the negative 1 outside. So that's making it a plus 3 times the cube root of 4 like that. So our final answer here is a 3 times cube root of 4. All right, but hold it. This is not the total final answer. This is only the final answer for our first integral over here. Okay, this first integral is of our 2 broken up ones. This one here is a 3 times cube root of 4. Okay, so I'm going to step over to my other board. And now, all right, so for my other piece of the integral right there. Now let's consider the improper integral from 4 to 6. And keep in mind an expectation that this should also converge. Okay, converge to whatever value that is, and we're on our way to find it out. So x minus 4 to the 2/3 in the denominator. Okay, so that means I'm going to produce this as a limits problem because I know that it's going to converge, so it's completely legal to have equal signs here. 1 over x minus 4 to the 2/3 power, okay, dx, but then this is an integral that we're accumulating from the t to 6, okay, and where now I'm going to take the limit, allowing t to approach 4 from the right hand side, okay, from the right hand side. Okay, and so now once again I'm going to do a little bit of substitution. My substitution work, I'm going to let I'm going to let u equals x minus 4 again. So x minus 4. So all that work I've seen earlier from the other half of the work was still there. So allow me to, not to get too far back into the details, but now the only difference here is that the u1 value will be t minus 4 because we're substituting t into our expression. And u2, the upper limits here, after we change the variable to u, will become 6 minus 4 will be 6 minus 4, which is 2. All right, and so now I'm going to keep this aside for now. That means in the next step, our integral becomes, so this bottom one here is t minus 4. This top one here is 2. And we have an integral now that's, our integral looks as following. 1 over u to the 2/3, okay, times du, because again, very same exact argument from the earlier work. I can the du here is a perfect substitution for the dx like that. And yes, we have to take the limits, allowing t to approach 4 from the right hand side this time. Okay, so now again I'm going to erase this extra work that I'm presenting here for the substitution, because mainly we just want to focus on the integral work itself. So now, fundamental theorem of calculus comes out again, and of course we are seeing this as u to the negative, so all of that here, okay, we're seeing that as u to the minus 2/3 power, u to the minus 2/3 power. So in that way, well, let's look at that. U to the minus 2/3 power. So once we found the antiderivative, just like how we did that in the other half part of the problem, we're looking at u to the positive 1/3, and then we multiply by 3. Okay, and then with this found antiderivative, I am going to substitute in eventually t minus 4 and 2 into that. But then the problem will still remain a limit problem by letting t approach 4 from the right hand side. Okay, so now that means in my next step, I am going to proceed with the fundamental theorem of calculus. So here it gives me 3 times 2 to the 1/3 power, okay, and it's a positive 2, and then I'm going to subtract, and then here I'm looking at 3 times t minus 4 raised to the 1/3 power, and now we realize that we have an expression completely in terms of t here. Now that first term is already a constant, not much to worry about. This is the only expression that's dependent on t, and then so here we are taking the limit, allowing t approaching approaching 4 from the right hand side. And so now in that way, I'm seeing that according to limit laws, this term right here will go to 0, and that term will remain in the same 3 times the cube root of 2. Okay, and so now subtracting the 2, so our final answer now is 3 times the cube root of 2. Okay, and so this is the answer for that particular problem, for that particular part of the improper integral. So now we are ready to put all the pieces together. Okay, so this first integral came out as a finite limit being 3 times the cube root of 4. So now I'm going to start erasing all of these extra work right here. All of these work that we have already done, and I left it here long enough. Okay, so now we are ready to conclude out our final integral. So the first improper integral here gave us 3 times a cube root of 4. And now I'm going to add with the result from the other piece. So all that here, 3 times a cube root of 2 is the answer for this other one. Okay, so now it's plus 3 times a cube root of 2. And I don't think we can factor out, I don't think we can do any better other than just factor out a cube root of 2, but it's not important. So this is our, at least that is our final numerical answer. So yes, it is now again clear that this integral is a convergence integral. And then now furthermore, it converges to this value right here. It has a numerical finite limit value. Okay.